Product was a DC to DC boost converter with current control. One of the benefits of current control is its immediate dynamic response, whereas a voltage control circuit has a delayed response. Current control circuits are optimal for constrained input voltage, such as our DC input voltage. Voltage control circuits are used for varied input voltages. One application of a boost converter is the Toyota Prius. This car steps up an input voltage of 202 volts to 500 volts in order to conserve room for batteries.
This is the ideal circuit diagram for a boost converter, with the input voltage being 12 volts, the inductor, the switch, which is going to be a MOSFET, diode, capacitor, and a load resistor. In our case, the input voltage is going to be 12 volts, and the output voltage is going to be at 32 volts with plus or minus 1% ripple. So it'll have 0.32 volt ripple on either side. The output current will be between 0.5 and 2 amps. Switching frequency needs to be between 20 kilohertz and 100 kilohertz, and we're going to choose 50 kilohertz for our switching frequency.
Parameters and these three equations, we're able to calculate the duty cycle to be approximately 62.5%, the capacitor value to be about 50 microfarads, and the inductor value to be 200 microhenries.
Here we have the duty cycle to voltage output transfer function, or as we more commonly know it, the transfer function for the power stage. So we have a few parameters here, Vin, which we know is 12 volts, the duty cycle. We have the equivalent inductance, which is found using this equation, the resistance, the capacitance. This little r is the resistance that we're going to factor in for the capacitor. This big R is capacitance, Le again. So we plug all these in, we get this beautiful second order transfer function here. We're going to move over to the Bode plots, which Chris will talk about, which is going to find us our cutoff frequency.
Here is the Bode plot of our power stage transfer function. As you can see with the phase, it starts at 360 degrees, which if we shift that to 0 degrees and find negative 90 degrees relative to that, it would be right in the middle of that steep curve in the bottom graph. This gives us a crossover frequency of around 530 hertz with a magnitude of around negative 235 decibels.
Here we have our standard transfer function for a controller. As you can see, there are 3 parameters, and we can use these 4 equations to find them. K-boost can be found using the ideal phi boost, which is around 60 degrees. Plug that in, we find the K-boost. For FZ, we can use the cutoff frequency that Chris just found divided by K-boost. FP, we can use the cutoff frequency again times K-boost. Then we move over here, we find the omega value by multiplying the frequency times 2 pi. We move down here to Kc, which is just omega z divided by the magnitude of GPS, which Chris also said is negative 235 dB.
So here is the Bode plot for our controller transfer function. At the top of the curve of the bottom graph, it can be seen that the crossover frequency is around 2.2 kilohertz. The magnitude at this frequency is around 255 decibels, and the transfer function is written below.
So finally, we have our transfer function for the loop, which is found by multiplying the transfer function of the power stage times the transfer function of the controller times the transfer function of the pulse width modulation times the gain of the feedback loop. Ideally, the gain of the feedback loop will be 1, and the pulse width modulation transfer function can be found to be somewhere around 0.0195. Now, for an uncompensated loop, the gain of the controller will equal 1, in which case the transfer function will be somewhere around the power stage with a different magnitude multiplied out front. For the compensated, this is where we use our actual transfer function that we found with the controller multiplied by the power stage transfer function, which we can see here.
So this is our Bode plot for the uncompensated loop gain. This plot is essentially the same plot as the power stage transfer function, except for it has a different magnitude. Here's the Bode plot of our compensated loop gain transfer.
After replacing the open loop clock input with a closed loop current control, we came up with this circuit schematic. If you look down in the bottom right corner, you'll see the current control mechanism. We used a PD controller. The P value was set to 0.08 approximately, and the derivative gain was set to about 0.24. after using the reference voltage of 32 volts, we came up with the following outputs that Chris will show you.
So this is our simulation of the output voltage. As you can see, the voltage waveform does not pass 32 volts. Here we have the zoomed in output voltage. As you can see, it stays within 1% of 32 volts.